Quantum mechanics is the branch of physics that deals with the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. It is necessary because classical physics cannot explain phenomena like electron orbitals or the photoelectric effect, where light behaves both as a wave and a particle. Quantum mechanics introduces concepts like superposition and entanglement, which have led to revolutionary technologies such as quantum computing and MRI machines. Unlike classical physics, which describes the world in terms of deterministic laws, quantum mechanics operates on probabilities and uncertainties. It challenges the classical notion of particles having definite positions and velocities, introducing the idea that particles can exist in multiple states simultaneously. This fundamental shift is encapsulated in principles like the Heisenberg uncertainty principle and the Schrödinger equation, which describe the probabilistic nature of quantum systems. Key historical experiments like the Double-Slit experiment and the photoelectric effect were pivotal in the development of quantum mechanics. The Double-Slit experiment demonstrated that particles such as electrons exhibit wave-like interference patterns, challenging the classical view of particles as discrete entities. Albert Einstein's explanation of the photoelectric effect, where light ejects electrons from a metal surface, provided evidence for the quantization of energy, earning him the Nobel Prize in 1921. Fundamental quantum concepts include superposition, where particles exist in all possible states until measured, and entanglement, where particles become interconnected such that the state of one instantly influences the other, regardless of distance. The quantum wave function describes the probability distribution of a particle's position and momentum, encapsulating the essence of quantum uncertainty. These concepts defy classical intuition, leading to phenomena like quantum tunneling, where particles pass through barriers they seemingly shouldn't be able to. Wave-particle duality is the concept that every particle or quantum entity exhibits both wave and particle properties. This duality is famously illustrated by the double-slit experiment, where particles like electrons create an interference pattern when not observed, but act like particles when measured. The de Broglie principle extends this duality to all matter, suggesting that every object has a wavelength, though it becomes significant only at the atomic scale. The double-slit experiment is a cornerstone of quantum mechanics, revealing the wave-particle duality of electrons. When electrons pass through two slits, they create an interference pattern on a screen, a hallmark of wave behavior, yet when observed, they behave like individual particles. This experiment highlights the mysterious nature of quantum entities, where observation itself alters the outcome, challenging our understanding of reality. The de Broglie principle posits that every particle has an associated wavelength, known as the de Broglie wavelength, calculated by the formula lambda equals h/p, where h is Planck's constant and p is the momentum. This principle extends the concept of wave-particle duality to all matter, suggesting that even macroscopic objects have wave-like properties, though imperceptible. It was a revolutionary idea that earned Louis de Broglie the Nobel Prize in Physics in 1929, fundamentally altering our view of the microscopic world. In quantum mechanics, probabilities replace certainties, with the wave function providing a probability distribution for a particle's position and momentum. This probabilistic nature means that we can only predict the likelihood of finding a particle in a particular state, not its exact location or velocity. This concept is central to quantum theory, as it introduces the idea of quantum uncertainty, where outcomes are inherently unpredictable until measured. The Schrödinger equation is a fundamental equation in quantum mechanics that describes how the quantum state of a physical system changes over time. It is crucial because it provides a mathematical framework for predicting the behavior of particles at the quantum level, encapsulating the dynamics of the wave function. This equation is the backbone of quantum mechanics, allowing scientists to calculate the probability distributions of particles, leading to insights into atomic and subatomic processes. The wave function is a mathematical function that provides a complete description of a particle's state in quantum mechanics. It encodes information about the probability amplitude of a particle's position and momentum, allowing us to calculate the likelihood of finding the particle in a particular state. The wave function's complex nature means it can exhibit phenomena like superposition, where particles exist in multiple states simultaneously until observed. In quantum mechanics, a probability distribution describes the likelihood of finding a particle in various positions or states, derived from the square of the wave function's amplitude. This distribution is crucial because it replaces the deterministic predictions of classical physics with probabilistic outcomes, reflecting the inherent uncertainty of quantum systems. For example, the electron cloud model of an atom uses probability distributions to depict where electrons are likely to be found around a nucleus. The wave function in quantum mechanics is a mathematical construct that influences physical reality by determining the probabilities of different outcomes. When a measurement is made, the wave function collapses to a specific state, dictating the observed properties of particles, such as their position or momentum. This phenomenon is famously illustrated by Schrödinger's cat, a thought experiment where a cat is simultaneously alive and dead until observed, highlighting the wave function's role in defining reality. Heisenberg's uncertainty principle states that it is impossible to simultaneously know both the exact position and momentum of a particle with absolute precision. This principle arises from the wave-like nature of particles, where measuring one property with high accuracy inherently disturbs the other, leading to a fundamental limit on precision. The uncertainty is quantified by the relation delta x delta p h/2, where delta x and delta p are the uncertainties in position and momentum, and h is the reduced Planck's constant. The inability to precisely determine both the position and momentum of a particle at the same time is due to their wave-particle duality. When you measure a particle's position accurately, its wave nature causes its momentum to become uncertain, and vice versa, as described by the uncertainty principle. This intrinsic limitation is not due to technological shortcomings but is a fundamental aspect of the quantum world, challenging our classical intuitions about measurement. Experimental evidence supporting the uncertainty principle includes the electron diffraction experiments, where electrons exhibit wave-like interference patterns, confirming their dual nature. These experiments demonstrate that attempts to measure an electron's position precisely result in increased uncertainty in its momentum, consistent with Heisenberg's principle. Additionally, quantum tunneling phenomena, where particles pass through barriers they shouldn't, further illustrate the principle's implications in real-world scenarios. The uncertainty principle fundamentally alters our understanding of nature by asserting that certain pairs of physical properties, like position and momentum, cannot be simultaneously known with precision. This principle implies that at the quantum level, nature is inherently probabilistic, challenging the deterministic view of classical physics. It suggests that the universe is not a clockwork mechanism but a dynamic interplay of probabilities, where observation itself influences reality. In quantum mechanics, superposition refers to a particle's ability to exist in multiple states simultaneously until a measurement is made. This concept is vividly illustrated by the quantum wave function, which describes the probability of a particle being in any of its possible states. Superposition is a cornerstone of quantum theory, leading to phenomena like quantum entanglement and the potential for revolutionary technologies such as quantum computing. A particle can exist in multiple states simultaneously due to the principle of superposition, where its wave function encompasses all possible states. This simultaneous existence is not just theoretical. It has been experimentally observed in systems like quantum bits, qubits, which can represent both 0 and 1 at the same time. The concept challenges our classical intuition, suggesting that reality at the quantum level is a blend of probabilities rather than definite outcomes. When a measurement is performed on a quantum system, the wave function collapses to a specific state, determining the observed properties of the particle. This collapse is a key aspect of quantum mechanics, where the act of measurement itself influences the outcome, a phenomenon known as the observer effect. The measurement process transforms the probabilistic nature of quantum states into a single, definite state, highlighting the interplay between observation and reality. Schrödinger's cat is a famous thought experiment illustrating the concept of superposition in quantum mechanics, where a cat is simultaneously alive and dead until observed. This paradox highlights the peculiar nature of quantum states, where particles exist in all possible states until a measurement is made. The experiment underscores the counterintuitive implications of quantum theory, challenging our classical understanding of reality and emphasizing the role of the observer in determining outcomes. Quantum entanglement is a phenomenon where two particles become interconnected in such a way that the state of one instantly influences the state of the other, no matter the distance between them. It was first theorized by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935, who described it as spooky action at a distance, and later confirmed through experiments by physicists like John Bell. This discovery has profound implications for quantum communication and cryptography, as it suggests the possibility of instantaneous information transfer across vast distances. Entangled particles exhibit a mysterious connection that allows them to influence each other's states instantaneously, even when separated by light years. This phenomenon defies classical physics, as it suggests that information can be transferred faster than the speed of light, a concept that challenges Einstein's theory of relativity. Experiments have shown that measuring the state of one particle immediately determines the state of its entangled partner, a process that remains one of the most intriguing puzzles in quantum mechanics. The existence of quantum entanglement has been confirmed through groundbreaking experiments such as the aspect experiment in 1982, which tested Bell's theorem. These experiments demonstrated that entangled particles violate classical expectations, supporting the predictions of quantum mechanics over local realism. The results have been replicated in various settings, including satellite-based tests, reinforcing the reality of entanglement and its potential for quantum technologies. Quantum entanglement raises profound philosophical questions about the nature of reality and the role of the observer in the quantum world. It challenges the classical notion of locality, suggesting that particles can be connected in ways that transcend space and time. This has led to debates about the interpretation of quantum mechanics, such as the many-worlds interpretation and the Copenhagen interpretation, each offering different perspectives on the implications of entanglement. Quantum tunneling is a phenomenon where particles pass through energy barriers that they seemingly shouldn't be able to, due to their wave-like nature. This occurs because particles exist in a superposition of states, allowing them to borrow energy temporarily to cross barriers, a process described by the Schrödinger equation. Quantum tunneling is crucial for technologies like semiconductors and nuclear fusion, where it enables processes that are otherwise impossible under classical physics. In quantum mechanics, a particle can pass through an energy barrier even without having enough energy to overcome it, a phenomenon known as quantum tunneling. This occurs because particles are described by wave functions, which allow them to exist in a superposition of states, including states where they have borrowed energy to cross the barrier. The probability of tunneling is determined by the barrier's width and height, with thinner and lower barriers increasing the likelihood of passage. Quantum tunneling has practical applications in various fields, including electronics and nuclear physics. It is essential for the operation of tunnel diodes, which are used in high-speed switching and amplification, and plays a crucial role in the fusion reactions that power the sun. Additionally, tunneling is exploited in scanning tunneling microscopes, allowing scientists to visualize surfaces at the atomic level with unprecedented precision. In the realm of semiconductors and quantum computers, Quantum tunneling is a key mechanism that enables the miniaturization of electronic components. It allows electrons to pass through thin insulating layers in transistors, which are the building blocks of modern computer chips, enhancing their speed and efficiency. In quantum computing, tunneling is harnessed to manipulate qubits, enabling the development of powerful computational systems that can solve complex problems much faster than classical computers. Energy quantization in quantum mechanics refers to the concept that energy levels are discrete rather than continuous, meaning particles can only occupy specific energy states. This is vividly illustrated in the atomic spectra, where electrons transition between quantized energy levels, emitting or absorbing photons of specific frequencies. The quantization of energy is a fundamental principle that explains phenomena such as the stability of atoms and the unique spectral lines of elements. Bohr's atomic model revolutionized our understanding of atomic structure by introducing the idea of quantum jumps, where electrons transition between fixed energy levels. According to Bohr, electrons orbit the nucleus in specific paths, and when they jump from a higher to a lower energy level, they emit a photon with energy equal to the difference between the levels. This model successfully explained the spectral lines of hydrogen, providing a foundation for the development of quantum mechanics. Quantum numbers are essential for describing the unique state of an electron in an atom, providing a set of values that specify its energy level, angular momentum, magnetic orientation, and spin. These numbers, including the principal n, azimuthal L, magnetic m, and spin s, quantum numbers, help predict the probability distribution of electrons, crucial for understanding atomic behavior. For example, the principal quantum number n determines the electron's energy level and distance from the nucleus, influencing the atom's chemical properties. Electron energy levels are experimentally verified through spectroscopy, where atoms absorb or emit light at specific frequencies corresponding to quantized energy transitions. When electrons jump between these levels, they emit or absorb photons, creating distinct spectral lines that serve as fingerprints for each element. The Rydberg formula accurately predicts these lines, confirming the existence of discrete energy levels and supporting the quantum mechanical model of the atom. Quantum mechanics has revolutionized modern technology, with applications ranging from semiconductors to MRI machines, fundamentally altering how we interact with the world. It enables the development of quantum computers, which leverage principles like superposition and entanglement to perform calculations far beyond the capabilities of classical computers. Additionally, quantum mechanics raises profound questions about reality, challenging our understanding and driving future scientific exploration. Quantum computers harness the principles of superposition and entanglement to process information in ways that classical computers cannot, offering exponential speedups for certain tasks. They use qubits, which can represent both 0 and 1 simultaneously, allowing for massive parallelism and the potential to solve complex problems like factorizing large numbers or simulating quantum systems. This technology promises to revolutionize fields such as cryptography, optimization, and drug discovery, pushing the boundaries of computational power. Open questions in quantum mechanics include the nature of wavefunction collapse, the reconciliation of quantum mechanics with general relativity, and the interpretation of quantum entanglement. These unresolved issues challenge our understanding of the universe, prompting debates over theories like the many-worlds interpretation and the Copenhagen interpretation. As researchers continue to explore these mysteries, they seek to uncover the fundamental principles that govern the quantum realm and its implications for reality. Quantum mechanics holds the potential to revolutionize our understanding of the universe by providing insights into the fundamental nature of reality. As we delve deeper into concepts like quantum entanglement and superposition, we may uncover new principles that could explain the mysteries of dark matter and dark energy. The future of quantum mechanics promises to bridge the gap between the quantum world and cosmology, offering a unified theory that could redefine our perception of the cosmos.